and welcome back to Physical Geology with Professor Farida Baksamusa. And today's journey is into the world of volcanoes. We'll uncover the secrets of how volcanoes form, the different ways they erupt, the hazards they pose, how scientists predict eruptions, and some fascinating Canadian examples, especially in British Columbia. So let's begin with the basics. What is a volcano? A volcano is any location where magma from inside the earth reaches the surface, or has done so in the last few million years. Volcanoes aren't always those dramatic mountains. Often, the action is hidden underwater. There are subaqueous eruptions beneath oceans or lakes and subaerial eruptions on the land. Most volcanism on Earth happens along the ocean floor at spreading ridges, forming vast new crusts without constructing the mountains we usually imagine. Now, volcanism in Canada. Canada is rich in volcanic rocks, with most eruptions being ancient. But only in British Columbia and Yukon do we find volcanoes that have erupted in the last 2.6 million years. We'll explore BC's volcanoes in more detail later. Now, why study volcanoes? Studying volcanism reveals how Earth evolves, how climates can suddenly shift, and most vitally, how to forecast eruptions to save lives and reduce risk. How do volcanoes form? By plate tectonics. Magma forms in three main plate tectonic settings. First, divergent plate boundaries. So usually I do this experiment with Oreo cookies in the lab, where if you take two Oreo cookies and you spread it away, and you'll see, the gap will be filled, and that'll be filled with your magma. Okay, so spreading ridges, plates pull apart, mantle rises and melts, creating mafic. We studied about mafic, right? It's more darker colored magma made up of magnesium and iron. Magma that erupts forming pillow basalts on the seafloor. For example, Juan de Fuca Ridge. Second type of plate boundary is your convergent plate boundary, where the denser plate, so if you're having your Oreo cookies, the one with the frosting, that will be more dense and heavy, right? So if you put that down and you kind of scrape it, you'll see that your Oreo cookie, the frosting forms like a mountain. That's also called subduction zones. Here, water is released from the subducting plate, causing the mantle above to partially melt. The resulting magma can interact with continental crust, making it more felsic and prone to explosive eruptions. Example, volcanoes of the Cascade Arc. So there's magma that comes up. When magma forms near the subducting plates. Third type is mantle plumes or hot spots. Like for example, Hawaii. Columns of hot mantle create volcanoes even far from the plate boundaries, forming islands over millions of years. Okay, so it does not have to be during a divergent, convergent plate boundary, but just magma coming out on the crust. Fourth is continental rifting. Crustal stretches forming fractures that release magma, being in northwestern British Columbia. Magma composition and eruption style. The composition of magma can be mafic, that is running low in silica, intermediate, or felsic. We did that in intrusive rocks lecture. Or felsic, that's thick, high in silica. Mafic magma, gentle, very effusive eruptions. Think syrup pours easily. In felsic magma, explosive eruptions occur when trapped gases burst out. Think bursting pressure in a soda bottle, right? The most dangerous eruptions are usually those where thick gas-charged felsic magmas build pressure beneath the surface, okay, and then boom. Now let's study types of magma. Let's see the images and let's say their key features and examples. So cinder cone, this small, steep, short-lived monogenetic, for example, Eve cone in British Columbia, the composite. Okay. So composite volcanoes, large, steep, built from alternating flows and debris, variable magma. Example, Mount St. Helens. Shield, wide, gentle snow, persistent flows of mafic lava. Great example in Hawaii, Mauna Loa. Large igneous provinces, vast, rare, mega eruptive plateaus. For example, Columbia River basalts. Kimberlites. Deep mantle diamond carriers, explosive and very rare. Okay, Ekati, that NWT. Now, volcanic hazards. Volcanoes can be spectacular, but also deadly. Hazards are direct, immediate, and indirect, longer term. Direct hazards: pyroclastic flows, scorching, fast-moving clouds of ash and gas, destroying all in their path. Lava flows, usually slow moving, destroy property, but people can usually escape. Tephra, that's ash falls, collapse roofs, harm breathing, disrupt air travel. Lahars, mud flows caused by mixing ash, debris, and water, can travel far and fast. Sector collapse and debris avalanches. Sometimes a whole part of a volcano fails. This is called sector collapse or flank collapse, and it can unleash vast debris avalanches. The most famous example occurred at Mount St. Helens in 1980. Weeks of bulging on north side of the volcano signaled magma building up. Then an earthquake triggered the catastrophic collapse of that flank, the largest observed slope failure in Earth's history. The rapid landslide released and depressurized the satellite magma chamber, causing an explosive lateral blast and a towering eruption column. Closer to home, Mount Meager in British Columbia suffered a massive slope failure in 2010. About 900 million cubic meters of rock rushed down the valley, one of the largest such events in Canadian history. Over the last 8,000 years, Mount Meager has experienced more than 25 large slope failures, some even bigger than the one in 2010. Lava flows, impacts and risk. Lava flows like those at Hawaii's Kilauea usually advance slowly, posing little risk to people but often devastating infrastructure. Roads and homes in the lava's path are unlikely to survive. Now, monitoring volcanoes and predicting eruptions. Modern volcanology is about prevention as much as understanding. USGS geologist Chris Newhall outlines 6 key gas signs of impending eruption. One is gas leaks, emission of water vapor, carbon dioxide, sulfur dioxide from cracks. Bulges, deformation, ground swells as magma pushes upward. Earthquakes, swarms of tremors as magma moves. Sudden drop in quakes can indicate magma is about to break through. Big visible bumps like Mount St. Helens before 1980. Steam explosions, superheated groundwater bursts through indicating magma is very near. Tools and techniques. Seismometers, we all know that, detect earthquake swarms beneath volcanoes, giving early warnings. Gas detectors, they measure sulfur dioxide, carbon dioxide and steam, both on site and remotely. Deformation monitors, tilt meters and GPS units detect even subtle ground swelling or movement. Combining these signals helps scientists accurately forecast eruptions, often providing weeks to months warning. As a result, surprise catastrophes are now rare, provided warnings are heeded by communities and governments. Volcanoes of British Columbia. British Columbia showcases several volcanic settings. The Cascade Arc Garibaldi volcanic belt, result of the subduction of the Juan de Fuca plate beneath North American plate. Principal centers: Mount Garibaldi, the Black Tusk, Mount Price, Mount Calais, and Mount Meager. The last major eruption in this belt was at Mount Meager about 2,400 years ago, sending ash as far as Alberta. The Anaheim volcanic belt, likely caused by a mantle plume. Rainbow Ridge is its largest with vividly colored rocks. Rift-related fields like the Wells, Great Clearwater and Northern Cordillera regions associated with rifting and crustal stretching. British Columbia's most recent eruption about 250 years ago at Tisiak's River Cone, whose lava and gas killed about 2,000 people. Notably, the Stikian region includes Mount Edziza, a composite volcano among chiefly mafic flows and cinder cones. Why study and monitor these volcanoes? Because volcanic hazards can be so disruptive both locally and globally. It's crucial to continue monitoring, research, and public education. Advances in technology, satellite sensors, networks mean the risk can be managed and lives can be saved. So let's now wrap up. Volcanoes are more than dramatic peaks. Most of the Earth's volcanism is hidden beneath the waves. Plate tectonics explains the where and why of the eruptions. The diversity of volcano types reflects geological processes. Hazards, especially pyroclastic flows, lahars, sector collapse, demand constant vigilance. With modern monitoring, surprise tragedies are far less likely if warnings are taken seriously. British Columbia, with its subduction zones, mantle plumes, and rifting areas, is a living laboratory for volcanic processes, one that's both beautiful and occasionally dangerous. Thank you for joining me on this exploration of Earth's fiery power. If you have questions and want to learn more, check out the resources. Make sure you read the chapter, you do your lab well, and then you can answer your lecture questions. And if you have any more questions, I can meet you over Zoom during my office hours or email me. Thank you so much. I'll see you in the next video.